Hello there. So while finishing up the last video, I realized that some people have fancier calculators than I do, and that it is possible to calculate a standard deviation on a calculator with the push of a button. However, some calculators are only fancy enough to allow you to calculate a biased or an unbiased version, but not both. So I thought it would be a good idea to go over how to convert between a biased and an unbiased standard deviation. Here we have the standard deviation we calculated for a population parameter in the last video. Since this is a population parameter, we don't really think in terms of biased or unbiased formulas. Since we have all of the information, it's not biased, it just is what it is, so we use the biased version if we were talking sample statistics. On the sample statistics side, since we only have a couple people or a couple responses or data points, and we're using those to estimate the actual standard deviation, we use a unbiased version because the biased version slightly, I forget if it's over or underestimates the effect. But we'll find out when we get through our calculation here. So, what are we going to do? We've got a simple formula. We'll just pull it off here. We have S is equal to sigma times the square root of n over n minus 1. There you go. So fairly simple. We'll draw that S in a little bit darker so it's easier to see on camera. So how do we do? First we've got to fill this in. Let's do that in green. So S, we don't know what it is. We're hoping to find it. It's equal to, we pull out that calculation. It's equal to 3.7. Sigma is 3.7 times the square root of n over n minus 1. We had 6 different data points, so n is equal to 6. And n minus 1 is just 6 minus 1, which is 5. Now let's go through our steps. So we have S is equal to 3.7 times the square root, and we're looking for 6 divided by 5 is equal to 1.2. Now we go on to the next step. We're going to take this and turn this into something else. So we're going to take the square root. It's equal to 1.095. This rounds to 1.1, so that's what I'll keep. I'll just put a times there for multiplication, times 1.1. And that is equal to, I'm clearing the calculator again, so I get this to match up with this. 1.1 times 3.7 is equal to 4.07. Alrighty. So we see this is larger. So going from biased to unbiased, we see that the biased version underestimates the variance among our sample. That the unbiased version corrects that underestimation, giving us a larger number. So off we go to the next one. To get from unbiased here to back to biased, let's note that. And actually, while we're at it, let's mark it up here too. Biased to unbiased. We're going to use sigma is equal to S times the square root of n minus 1 over n. And we off back to green. This means we're going to take sigma is equal to 4.07 times 5 over 6. We got these numbers from right up here. we're going to take 5 divided by 6 is equal to 0.83. None of those are high enough to round, so we're just going to keep it as 0.83. We're going to take the square root of this, again, clearing the calculator so things match up. 0.83. Just going to give us sigma is equal to 4.07 times 0.91, and none of those are high enough to round, so we leave it there. So we're going to have 0.91 times 4.07 is equal to 3.7037. And none of those are high enough to round, so we end up with the 3.7 we had at the beginning. So let's go ahead and pull that out. You see, this is fairly accurate in its conversion, and in this case did not lose too much information, or really, in fact, any noticeable information to the rounding I did at intermediate steps in this process. So overall, pretty good. Pretty good. I hope this has been helpful for you and adds another tool to your belt. Let me know if you have any questions about how this worked or anything else.